Let's now do a quick example illustrating the Nyquist criterion, and because it's topical, let's do an example about disease spread. So let's suppose we have a population in which everyone is either susceptible to a disease, infectious currently, or they've already recovered. And if you're susceptible, you can become infectious, and if you're infectious, you can recover. And probably the simplest and most famous model that tries to capture the dynamics of this spread of disease and transferring people from susceptible to infectious to recovered is the SIR model. And the SIR model looks is a set of three equations. For our purposes, there's one equation that's particularly important, and that's the one that governs the size of the infectious population. And that equation is I dot, so the rate of change of the infectious population over time, is equal to beta, and then we have a product, we have the size of the susceptible population, and then normally you put the size of the infectious population in here. I'm going to put I mix instead. So this is not the whole infectious population, this is just those people who are infectious who are actually out in society and spreading the disease. So this is a minor modification, and then here we have a minus gamma I. And loosely speaking, these two terms are driving the two rates you see in this picture. This term here, this is driving a change from susceptible to infectious. This is driving the size of the infectious population up. And this gamma I, this is driving people from infectious to recovered. So gamma is like a recovery rate parameter. And just to give an idea of what this model would predict, well, if we say I mix is equal to the infectious population, so we're not, everyone who's infectious is just mixing, then if this is the size of the infectious population and this is time, then this model will predict a period of exponential growth. So given a very small initial infectious population, it will predict that you initially have a period of exponential growth and then it will die off after some time. So why did I put I mix in? Well, this is where our feedback is going to come in. So we're going to say that not only are people aren't just free to keep mixing. If we find that you're infectious, we're going to quarantine you. And how are we going to do that? Well, Q is going to be our control variable, and we're just going to do some simple stability analysis of a kind of a naive control policy. So I mix is equal to everyone who is infectious minus those that we quarantine. So this is our model for the process of disease spread, and if Q is equal to 0, we get this period of unstable growth. And what we want to investigate is some simple feedback laws for quarantining people, or some properties of simple feedback laws, and try and predict whether they would be able to stabilize this period of growth or not. So we need to turn this into a transfer function, which means that we need to linearize and take Laplace transforms. So linearizing first, we find that if the initial infectious population and quarantine population are both very small, then these equations here can be linearized to give I dot is equal to beta. And let's just assume that everything is normalized so that the size of the entire population is 1 unit. So if we start off in a situation where everyone is susceptible and the number of infectious people is very, very small, then we can approximate this first equation by beta, and then just I mix, which is I minus Q, and minus gamma I. And I encourage you to check this linearization for yourself. It's very quick to do. And now we take Laplace transforms. So Laplace transforming this, we get SI. We're in a bit of trouble because we've used capital letters for everything, even in the time domain. When you get used to doing these things, you don't even need to use different variables for your time domain and Laplace domain variables. Yeah, so apologies for doing it here, but well, we've come this far, so let's continue. So this is the Laplace transform of di by dt. I0 is the size of our infectious population at the beginning. We're assuming this is a very small number. And then this, and then all of this, when we Laplace transform it, we just get variables and constants. In particular, we get beta I, let's put the s's in, minus q of s minus gamma I of s. And now if we rearrange this, we will find that I of s is equal to, and then 1 over s minus beta plus gamma. And then this is all multiplied by I0 minus beta q. So here we can see how the size of the infectious population depends on how we're quarantining people and also the initial condition. So let's just start to draw that in a block diagram. And what do we get? Well, we have a beta. Let's put a minus sign here. Plus, and then we have an I0. And then here we have our process, which is 1 over s minus beta plus gamma. Here we have the size of the infectious population. And this isn't exactly right, so we should have a minus sign here, but I'm just going to put it in the feedback loop. So this equation doesn't match exactly this, but it will when we close the feedback loop. We just need to determine how we're quarantining people, and this is where our feedback comes in. And so there's many ways you might think about modeling the process of quarantining infectious people, but maybe certainly a simple, maybe a natural one would be to say that q is equal to alpha I of t minus capital T. So that is, we quarantine people if we discover that they're infectious, and our mechanism, let's say a test or something, it doesn't discover everyone who's infectious, it only discovers some proportion alpha of them, and it doesn't happen instantly, it takes a period of time capital T to do this. So we quarantine those that we discover with our test, and our test captures alpha proportion of people after a period of time t. And so if we Laplace transform this, we see that q is being decided by a feedback mechanism. And in particular, remembering that the Laplace transform of a delay just gives you an e to the minus st, we have an alpha e to the minus st. And we now have a feedback representation of this simple model for the spread of a disease and a system designed to prevent that spread. So, will this system work? What does the Nyquist criterion have to say? Well, we now have everything, we know everything that we need. So let's just apply the Nyquist criterion and see what we get. So to apply the Nyquist criterion, we need to draw the Nyquist plot. And what is the Nyquist plot? It's a plot of L of s. What is L of s? It's everything that's in the feedback loop, ignoring 1 minus 1. So you have a negative feedback convention, so you always omit 1 minus 1. Sometimes people even put the minus 1 in the, like whether at some point in one of these plus symbols, but we've got our minus 1 clearly on display. So for us, L of s is the product of everything in the feedback loop. So we have a beta e to the minus st, you've got an alpha, and then this is all over s minus beta plus gamma. So what does this Nyquist plot look like? Well, I encourage you to go away and check things on MATLAB or have a go at plotting it by hand yourself. But let's just get a few points on here. So as s goes to infinity, the size of L of s goes to 0. So this term on the denominator gets much bigger than everything else. So L of s is going to 0 as s goes to infinity. And also as s gets large, so s is equal to j omega, if I make omega very, very large, we have the effect of this term causes us to wind in to the origin. So as omega gets large, L of j omega looks something like that. So it starts to spiral in, and delays always cause clockwise spiraling. How about when omega is equal to 0? Well, when omega is equal to 0, that term becomes 1, that term becomes 0, and we get alpha beta over gamma minus beta. And beta is always a bigger number than gamma. If that's not the case, then the disease doesn't spread exponentially. So, well, maybe it's not always the case, but there's certainly no need to control the disease if that's not the case. So what this means is that when omega is equal to 0, it's equal to some negative value. And then if you go away and you try some other parameters and you plot things together, we get some plot that looks like this. So this is L of j omega for omega greater than or equal to 0. So we're almost ready to apply the Nyquist criterion. But we know from our last lecture that in order to apply the Nyquist criterion properly, we don't just need the plot for positive frequencies, we also need it for negative frequencies. But we get the plot for negative frequencies just by mirroring in the real axis here. So the full Nyquist plot just looks something like that. And now we're ready. And so let's say -1 is there. So the Nyquist criterion says that the number of open loop unstable poles is equal to the number of closed loop unstable poles plus the number of anti-clockwise encirclements. Do we have any open loop unstable poles? Well, if beta is greater than gamma, then we have one unstable open loop pole. So number open loop unstable equals 1. Therefore, we need one anti-clockwise encirclement in order for the closed loop to be stable by the Nyquist stability criterion. Do we have that? Well, we look at our picture here, and remember, it's no problem in this case. To count encirclements, we take our point, we draw a line out, we see how it cuts, and we see that we have one anti-clockwise encirclement. So we discover that the number of open loop unstable poles is equal to the number of anti-clockwise encirclements of the Nyquist diagram. And therefore we conclude that the system will be closed loop stable. And so a little challenge for you is, okay, for particular values of alpha, beta, gamma, and t, we seem to be getting an anti-clockwise encirclement. For what ranges of values do you think this will continue to hold? What will happen if we make the time delay very, very long? If we send t to infinity, what's going to happen? What happens if alpha is very, very small? So that would mean our test is very ineffective. Will we still get an encirclement, or will the point that crosses through the negative real axis, will it move in some way that will make us lose an encirclement? So a little challenge for you is you've got all the building blocks here. Just maybe have a little investigation and try and make sure that everything checks out common sense-wise in terms of the predictions of this simple model about whether or not our quarantining process will be effective at regulating the spread of disease. So there we go, a little example.